Now, have I solved the planning problem? No, not at all. So why did I do this? To make a heuristic function. And in order to make a heuristic function, now let me say what the heuristic should be. So I'll again not stick out with this specific example, and what I will stick out is that I'll directly write down the heuristic for a dummy problem. So the first level, the first heuristic is what is called as the max level heuristic. So suppose my goal was A and not B and C and not D and not E. I say the first level at which A is to be found in my planning graph is 3. It did not occur at level 0, it did not occur at level 1, it did not occur at level 2, level 3 it could occur. Not B was first found at level 2, C was first found at level 2, not D was true at the source itself, it was first found at level 0, and not E was found at level 1. So my max level heuristic says and that is true. Why? Because if you look at it, what I've done is, starting from a source, I generated a lot of children. I took a union of all of them. I generated a lot of children. I took a union of all of them. So every permutation and combination by which every little could be obtained is here. Every permutation combination by which every little could be obtained is over here at level 2. That's at level 0, level 1, level 2. I didn't find A here. I didn't find A here. That means no single action can get me A. I didn't find A here. That means no two actions together applied can get you A at a level of 2. I found A over here. That does not mean by applying 3 actions one after the other you can get A. It may be mutex. It may not be practically possible. However, that's saying there is some possibility. It may still not be possible to produce A at level 3, but there is some possibility if the actions don't naturally have mutex with each other, which your algorithm couldn't find out. We're not finding every mutex. We assumed 2 actions can be simultaneously applied. Our planning is linear, only 1 action at a time. So A may have been produced by applying 3 actions in parallel here, 2 actions in parallel here, 2 actions in parallel here. So the actual depth will be 7, 3 plus 2 plus 2. But it's admissible pessimistic estimate, and that's why my heuristic is admissible. So that's exactly what I do, that by saying that, what's my relaxation? My relaxation is you can apply actions in parallel and just check for the mutexes. And by doing that, I said that the first level by which I get A is 3. It means it's not possible to get A at level 0, 1 or 2. It may not be possible to get at 3, but it's admissible. I'll always underestimate, I'll never overestimate. The second one is using a very own carry forward from the last lecture. So for the same example, it says that you assume subgoal independence. It means while producing A, I'll not magically produce C or a not D. While producing not B, it will need its own actions. I'll not get a A or a C magically. While producing not E, I'll not get a not B, A or a C magically. Every subgoal A, not B, C, not D, not E is independent, and its own set of actions will achieve it. There may be negative interference. While achieving C, I undid A, so I'll have to get A, but it doesn't have an interaction that by getting C, I automatically get A and not B. That means applying a minimum of 3 actions will get me A. It can be higher. Applying a minimum of 2 more actions will get me A and not B. It can undo A that you need to re-establish, but best case it won't. +2 +0 +1, 8. That's a sum level heuristic. And the last heuristic is what is called as the set level heuristic. So one thing we haven't done so far is to look at mutexes. So the set level heuristic says at what level do I first get all subgoals? This is max level heuristic. At what level do I get all the subgoals? That is max level heuristic. So I add a constraint such that no 2 subgoals are mutex to each other. And then you could just look at it. So let me draw in a very quick planning graph for that. I cannot use the past one because I didn't draw all mutexes. So let's say that I have got A and B over here. I of course apply the persistence action A, B, and I apply another action A1 that gives me a C. And let us say that there are mutex relationship around over here. So they end up being mutex relationship over here. My goal is A and B and C. So first level I do get A, B and C, but they have mutex to each other. And magically what happens is that persistence actions, the same action A1. And what happens is that there is another action A2 that also gets me A, and A3 that also gets me B, and now they are not mutex to each other. So the first level I get A, B and C is at 1, but the first level I get A, B and C without mutex is 2, so the answer is 2. The first level I get A and B and C such that neither of A and B and C have a mutex relationship to each other. Does it turn out to be an interesting heuristic? No. Sum level heuristic is not even admissible, and we've already seen that there are no negative interactions modeled. Mutex is extremely rudimentary. So it's not that good a heuristic as well, even though it's linear. So where do I go? Where did we teach this? Now what I say is that I expand my aim further. And by saying that I expand my aim further, I say I will try to extract a solution from this planning graph. It's somewhere hidden. And let's see if we can do that. So coming back to my older problem right here, so what do is A0 and eat cake have a mutex with each other, so I can only select one of them. That's a constraint. Let us say I select this one, I select the eat cake. That means I cannot select this persistence action as well. Using it, what do I get? I get the effects of this action and I get the effects of this action. Now what do is, these are mutex, so I can again have one of them, and the precondition also needs to be active. So virtually I've got only one of these over here. And Now what do I do is, again I select some of these subsets such that I only select the ones which are non-mutex to each other. So my problem is to extract a solution. My problem is that I need to select one actions out of every two actions that have a mutex to each other, and if I select an action, the precondition of it has to be true. If I select an action, then its effects also have to be true. Guess what? This is nothing but a constraint satisfaction problem. So I say try to extract a solution is a constraint satisfaction problem where mutexes, preconditions being applicable, and effects are constraints. Now I'll make you remember it virtually again and again. So what's the biggest thing to happen in AI? Excellent constraint satisfaction problem solvers. As a heuristic, nobody would have taken this approach seriously. However, constraint satisfaction problem, everybody takes it absolutely seriously because they are excellent solutions where you give a constraint satisfaction problem and it gives you whether it is solvable or not extremely quickly. Fails happen first, great heuristic, generalized heuristics. And if a solution is possible, it gives you extremely quickly. We didn't cover all the heuristic, but there are excellent heuristics for that. Now, what might happen is, so just take this graph as, planning graph as, everything needs to be colored as black and white. So it's not RGB, it's black and white, which I had it as yellow and transparent. And you just need to color them up adhering to all the constraints given and solve it up. Now what might happen is that you may not be able to get a solution, not because of the fact that CSP has given you a wrong output. Why did we stop at level 2? Because it leveled off. It leveled off because states were repeating. However, CSP may be able to solve the problem only when the graph is more deeper. So maybe till level 2 my CSP fails, level 3 my CSP fails, level 4 my CSP fails, level 5, 6 my CSP fails, level 7 it succeeds. And that is the new iterative deepening problem. So my new iterative deepening kind of a problem is intuitively algorithm being called as a graph plan algorithm. So I first go, so state 0, action 0, state 1. I see extract solution. Succeeds, great. Fails, I repeat the same thing. There's no memory constraint, you can just add it on top of it. I'm only doing it for illustration purposes. Extract solution. Fails, no problem. Go one more level. You can just add it to that level. You don't need to go to another level. And remember, this is state level 0, action level 0. It's not a particular action applied on a particular state. Extract solution. succeeds, and extract solution will give you what is the output. There's one little trick that you can play around over here, which is till set level heuristic, you know that there is no solution. So I could first expand graph till set level heuristic. So I first expand till set level heuristic. Then I see extract solution, false, expand one more. Extract solution, false, extract one more. And so on till you get a solution. So the algorithm is same as iterative deepening. You go till set level heuristic, that's your initial guess, and then you keep on expanding one by one, and then you try to extract a solution. Each extract solution is nothing but a constraint satisfaction problem that tries to select actions with the mutexes, preconditions, and effects as the constraints. If that succeeds, then that's good. Now, there are two things that you would be concerned about right here. The first one is that is the algorithm complete in terms of when there is no solution? Can this algorithm find out? The excellent thing that can happen is that if set level heuristic is infinite, means till leveling off, at least one pair of subgoals are mutex, and this of course means that there is no solution. If there is no solution, just return infinite, no plan, null plan, whatever. But not always will the problem be that easy. Sometimes the subgoals may be non-mutex to each other, but still there may be no solution possible. Now the constraint satisfaction problem, it turns out, is actually a more involved algorithm, not the way that we saw it. It doesn't only give you whether a solution exists or not and a solution in case it exists. It also gives you a third thing. If the solution fails, it gives you something that will enable you to trace it. It tells you which is the least number of subgoals which are not reachable, called as the no goods. So which of the vertices you cannot color, which of the literals you cannot produce, which of the variables cannot be assigned values, it's no goods. And as I go level by level, I generate more deeper graphs, I generate graphs for more amount of time. What really happens is that there are more options to generate literals. So not only do the constraints break, but the literals which are realistically achievable by this constraint satisfaction solver, trying to find out an actual solution, they reduce with times. Once you consistently get some variables cannot be assigned a value, you just say it's enough. If these variables cannot be assigned a value, then there is obviously no solution which is possible for the specific problem, and you could just break from there. So the beauty of it now lies that the algorithm is absolutely simple. Planning graph, what could be the complexity? So let's come to the planning graph again over here. What could be the complexity? I need to generate some level. So let's find out the complexity for one level. The number of levels will assumably be small. So at one level, what do? My list of actions are, say, A. I just say if the precondition is valid or not. This can be indexed, so constant amount of time lookup, and then I just apply a action a amount of time to generate L literals a plus L amount of time. So the planning graph itself doesn't take time. What takes time is adding these mutexes, and let's say they are n literals, so they could be n plus n to n, which in complexity theory will be written as n names that you see over here and literals that you see over here, and what happens around over here is that they are over here also a actions, and I consider in the interaction between all the literals which are over here represented. So here they are a total of 2n entries in complexity written as n, and n square number of constraints are possible, n square mutexes are possible. What happens around over here? Here each one of these literal will have a persistence action. That means n actions already, and you've got proper actions like eat cake, bake cake, which are a in number. So n plus a the whole square mutex is possible. This is the complexity to check out if two relations have a mutex to each other or not, and of course that multiplied by the maximum level that you go is what becomes a complexity, which is polynomial. It doesn't mean that I have converted exponential planning problem into a polynomial over here. So there is a plus CSP over here. If I write down the complexity of CSP, it will be exponential, but we know because of excellent heuristic, the complexity remains exponential, but the real feel of it happens to be much less than an exponential. So CSP solvers in reality, they fail fast, they succeed fast, and they give you no goods which are absolutely very fast. That is what makes in this algorithm as something which is absolutely very special.